Hello, still Monday, November 27th, 3:30 in the afternoon. I thought we could just get started on problem 10. As you can see, the light is dimming. Dusk is already, I don't know if it's dusk, it's perhaps rather totally overcast that causes it. Well, I had the idea while solving problem 9 that it was an auxiliary problem, and maybe we're going to use it right now on this function. So we define f of z this way, and let's try to, that's the same guy we have up here. Yes, it is. So let's try to make the Q expansion of f of z. I'll just write it to make sure that I have the right expression. Right. For z, that means Q is Q to the 4th. So it's Q to 8/6. That's 4/3. And down here it's Q to 12. That's Q to 1/3. That's 8th to the 8th. And the Q minus Q squared to nth to the 4th. That's Q to the 1st. And then we can divide this up to this. I think I read that somewhere in the problem, didn't I? Oh yes. That was here. Right. So that means it has the right form to be a modular form, or even I forgot what it is in English. A Spitzen form, having 0 at infinity at least. But let's see what it does at the other. At 0, that's the other spot. Well, let's wait a little with that. Oh, we have to prove that it lies in gamma naught. So I believe we should use problem 9 and work on. Well, this is actually the start of A. F of 1 divided by 4z. 1 divided by 4z, that's 2z we end up with. And then we use the transformation formula. And that's 2z divided by imaginary unit eta of 2z to the fourth. So it's set to the fourth. That gives unity, and that gives square root I to the fourth. That gives -1. How about the number 2? That gives 4. Z squared. And then what about this? Yes, we should get back to f. This seems not to be likely. Let us see if k from problem 9 comes out anything. It's -4z squared to the first. Well, that makes sense. But it should have been 4 in the numerator, not the denominator. Well, I don't know how to come any further along that line. Then let's work on the value of the cusp at naught. Like this. That was a substitution, and then it's -1 squared. That's, of course, unity. So we use the transformation formula. Square root z divided by 4i to the 8th. Z divided by 2i to the 4th. Add of z halves to the 4th. This is very weird. It's z to the 4th divided by z squared. 2 to 4th divided by 4 to 8th. That gives like 2 to 24th in the denominator. And this is a minus once again. So I had expected z to vanish, because then we won't get a nice Fourier transform at infinity. That is at naught. Of course, this works out nicely. The fourth root of q and q to the 8th divided by q to the 4th. That, yeah, we have to do that. It'll probably work out correctly. But everything is ruined by z squared here. Well, we had to prove a few things. The translation, then I can at least look at the translation of by z of f of z plus 1 and see if I will have any success there. Then we shall go back to the power expansion here. So that, yeah, the power expansion shows that it's periodic with a periodicity of 1. Q, the new value of Q is just Q again. So that's 1 out of 3, but that was the trivial one. I thought we should just work a little more on the problem. Now it's Wednesday, November 29th. First of all, capital F was actually defined like this function. So I think we should call it minuscule f instead. And next, if we apply the definition here, the powers of q cancel, both being to the 8th, it's 1/3 cancelling, and then we get a product here. That may be reducible, I can't just see it though, but we still retain 4 in the denominator, and it should be in the numerator. So I don't see how to work further on this. Then I hallucinated here that S had unity in the diagonal and not in the lower left corner, meaning we get z to minus squared, or you know what I mean. And then it cancels here. So we just end up with unity. And now we can work, substitute here, q to, oh, it's the 4th root of q we get, that's the square, that's q to 1/12. Oops. Q4 to nth, and in the denominator we get Q12 to 1/12 again, so they cancel, and then it's Q2 to nth, to 8th up here, and to 4th down here. And we will just reduce it. Just leave it. We make the power expansions of the denominator and get a series starting with unity, and then I think for Q2 will come up here. Oh, but that's the lower power of Q4. So I don't know what comes really. Then never mind. It will have the right form. So we have found the value of at the cusp f of naught is -1 divided by 2 to the 6th. At the other cusp, which I forgot the other day, that's -1/2. I wonder if we could be smart and translate it to naught. That's creative, isn't it? By using square root t. And then s. This is not an SL2, of course, but because of this rational number. But let's see what we get. And I should begin to learn that this is whether it's a row or I'll just have to do it by hand. Naught -1 unity and 1/2. We just multiply it by 2, 1/2, 1. And of course we can see immediately that -1/2 is mapped to infinity here. But oh, it has the wrong determinant. So that I wonder if that's a problem. So I was creative enough to get this idea, but I like the technique of pulling it through. The matrix we could use, of course, by completing this guy. to 1, or it may be simply this guy. It's just as simple to work on as the other ones. So let's just use this guy, alpha, instead. Now that's becoming complicated. I would rather not have to work on that. We just try and do the stuff up here, see if anything sensible comes forth. And we should compare this expansion with this. And that seems very hopeless, because at infinity this tends to unity, and this guy tends to naught. So this idea doesn't work at all. Good morning. Having tried various tactics, I decided to work on this. I actually did it after having attended my dance lesson, and the result is here. I admit that this is just too large a computation to make on a tablet, so I did it by hand, and I actually ended up, so it's the matrix mapping minus 1/2 to infinity, and then we get this value at the cusp times, already here we can see it will give a power series in Q. So I applied the definition of F, and what did I do then? Then I used the transformation formula for eta and reduced the arguments, and then we performed the translation, giving this. Then we end up with this, and being able to use the transformation formula once again. And I thought some reductions here. I didn't find much really, but then I expanded, used the definition of eta as a power series, and then the odd power of Q actually vanishes, so it just becomes a power series, and the value at the cusp is 2 to minus 4th. Next, my only idea is to actually perform this transformation on F and see if we can prove invariance by it. These two are already okay. And we use the definition. Which I forget this morning. Was it n to the 8th of 4? I need my glasses. We must use the transformation formula. So we let this be z and then put this to the other side. This is number 2, of course. Oh, and this must be raised to the 8th as this to the 4th. So we trot on. 4z to minus second, 4z to 4th, that's 4z plus 1 to squared. And that's what we have here in the denominator, so they cancel. Next we have z to minus 4th and z squared. That gives the inverse square of z, and then the imaginary unit to 8th, square root of it to 4. The imaginary unit raised to the 4th power gives unity, and this one minus 1. All right, and then the transformation formula of eta. It's these guys don't change, so it's only this guy that we need to worry about. Oops, this is to the 8th and this is to the 4th. I keep forgetting that apparently. So this is translated to the left. How do we do it? If we just take q24th, the 24th root of q, then this is minus 8. And this is transposed 2 to 4th, that's plus 8. Oh, they cancel. How very nice. now we can just apply this guy. So it's square root 4z divided by I to the 8th, square root 2z divided by I to the 4th, they must be divided, times eta to the 8th of 4z divided by eta to the 4th of 2z. This is z squared divided by z to the 4th divided by z squared. So all the z's cancel, and I to the 8th gives unity, I to 4th gives minus, so the minus cancels. So it's just the constant here, 2 to 8 divided by 2 to 2 squared, that's 2 to 6. That reminds me, that was exactly what came earlier on in the other computation. So did I do something wrong with the constant here? This is 2 to 8 divided by 2 squared. That gives like 2 to 6. So 2 cancels as well. Thereby we are left by something in the eta function itself. And then we shall see if we can rewrite it as f in some way. Oh, that's actually the definition of f itself. My God. Had I known from the onset that we needed to go through this, then it had been much easier. I believe this solves problem 10a.